To use the testmeansC function, you have to use either the x1 and x2 arguments or the dv and iv arguments. Use one set of arguments or the other, but not both at the same time. If you're using testmeansC for a one-sample hypothesis test, you'll use the x1 and x2 arguments. But if you're doing a two-sample hypothesis test, whether you use x1 and x2 or dv and iv depends on the nature of the problem, as we'll see in this video. The testmeansC function has some standard optional arguments. With testmeansC, you have options to weight observations, specify the dataset name, the number of digits to display after the decimal point, and whether you want results printed to an HTML file in your working directory. The function also has some unique optional arguments that you might use for two-sample hypothesis tests. I will show you how to use the optional arguments named var.equal, paired, pop.sd, and var.test in this video. By default, testmeansC will report the 95% confidence interval of the difference of means, but you can modify the confidence level using the ci.level argument or suppress the CI table by setting the ci.table argument to false. By default, testmeansC will plot the difference of means and its margin of error to help you visualize your difference of means test. You can fine-tune its plot using the main, xlab, and xlim arguments, or suppress the plot by setting the ci.plot argument equal to false. To learn how to use the testmeansC function, let's work through some examples. Okay, so the testmeansC function is used to run difference of means tests in different varieties. The most basic flavor of the test is a one sample test where we're testing the mean of a sample variable against some hypothesized value. It would look something like this. We would type in the name of the function testmeansC, and use the x1 argument and set that equal to a variable in the data set. Let's say I was looking at life expectancy for females. What I might do is compare that to a hypothesized value, let's say 65. So this is setting up a test whether the average, country level average female life expectancy is different than 65. So it's outputting our results here that we can see. It gives us a table of results comparing the observed value of female life expectancy to the hypothesized value of 65, giving us descriptive statistics, the t-test statistics, and we can see here that the t-statistic is quite large, 8.14, so the p-value is less than 0.05. It generates a table of the confidence interval of the difference of means, so the difference between the mean and 65, and when I hit enter it will plot the difference of means, the 95% confidence interval for the difference of means. So it's plotting the value 6.72 with the confidence band, the bands extended on either side to represent the confidence interval of the difference between average female life expectancy and the hypothesized value of 65. So that's the simplest version of the test. Now to show you a couple of variants that is still using the required arguments. One variant, I call it the x1 versus x2, which is we have two variables and we're comparing the means of the two sample variables to each other to see if they're significantly different from each other. So in this version of the test, we would specify an x1 variable and also specify an x2 variable. So let's stick with the variable I used for the first example, female life expectancy, and compare it to the male life expectancy and see if they are significantly different on average in countries around the world. So it's going to compare the average of female life expectancy to the average of male life expectancy. In the first example, I set the x2 to a specific value. In this next example, the two-sample test, I've set x2 to a variable. Let's run this and see what it looks like. We've got several items to look at. It tells us our testing framework. It gives us descriptive statistics. The mean female life expectancy is 71.72, male life expectancy 66.86. It's at the country level around the world. We've got our t-test statistics comparing the difference. We observe a difference of 4.86 years, standard error of 1.11, so it has a t-statistic of 4.37, which is significant at the 0.05 level. The p-value is very small. We've got our table, and if we hit return, we'll get a plot. The plots are going to look very similar to one another, but the axis values change. So it's given us, again, the confidence interval for the difference of mean estimate. The difference of means estimated 4.86 years, but to be 95% confident that the interval contains the true difference in the population, our bands extend from 2.67 to 7.05. So this is indicating that there is a statistically significant difference in mean life expectancy between males and females in countries around the world. Okay, so that example, the x1 versus x2, compared two variables that were very similar to one another, but different because they would be on different groups. So like both of those, the example, the x1 versus x2 test, both of them were measures of life expectancy in the variables. One was for females and the other was for males. The final basic variant of the testmeansC function follows a slightly different logic. So the x1 variable, we're now using the dv variable to run this out. So the dv variable is some interval level measure in a data set, such as, I'm going to switch this to life expectancy in general, the average males and females both included on the country level. So that's the dependent variable, and then we could use the IV argument to specify a binary variable that separates the values of the dependent variable into two groups. For example, I have a binary measure of democracy in the data set. I specified it there. And now if I run this, I'll get a similar looking means test, and it's still called a two-sample test because we've divided essentially our sample into two groups. We've divided the sample into democracies and non-democracies. The results give us the framework and assumptions we're using. It tells us that in non-democracies, the mean life expectancy is 68.57 years. In democracies, where the value of the eiu.democ.bin variable is yes, mean life expectancy is 77.72 years. We've got a table of t-test statistics. The difference is minus 8.7 years. The t-statistic divided by the standard error gives us a t-statistic of almost minus 9. It's a very small p-value, much less than 0.05, so that is a statistically significant difference. We've got a table reporting the confidence interval, and again, if I hit return, I'll see that on a plot. So if the point value is the difference of means, that's the point value of the confidence interval, and it extends on the low side to minus 10.62 and extends on the upper side to minus 6.78. So suppose someone asserted that life expectancy was the same in democracies and non-democracies. We've tested that hypothesis and would reject that hypothesis because the p-value of the test is less than 0.05. The confidence interval does not contain 0. So it appears that there is a statistically significant difference in life expectancy, and we can see from the descriptive statistics that life expectancy on average at the country level is higher in democracies than it is in non-democracies.